Geotechnical Engineering, Part A, Soil Mechanics, Chapter 12, Soil Consolidation. So in consolidation, in previous video, we talked about the process of consolidation, which delta sigma, when you apply a stress on pressure on the soil, it initially applied to the water, and by times go on, delta U disappears and delta sigma prime is developed. So the process of translation of delta sigma to delta sigma prime called consolidation. So consolidation is a reduction in volume due to increase of stress when you apply a pressure on the soil layer in a saturated soil with low permeability. So definitely K should be small enough. Call that to consider that like a consolidation, which ends up to drainage of poor water soil grains, and the outcome is reduction in thickness of soil layer. We call that a consolidation settlement. S sub C stand for a consolidation settlement which is consolidation. We have other kind of settlement like immediate settlement in like rain and gravel and sandy soil, which has high permeability. So is a sudden immediate settlement. That is not considered like consolidation. And a graphical view of consolidation, if you apply a load on the surface of our soil, and initially that extra stress applied to water, and by time it just translates from water to soil grains, and it's just a time consuming process, and we call that consolidation. So this is a graphical representation what's happening in consolidation in soil. And let's go to mass and derive some formula for consolidation. So if you just consider a three phases of a soil layer, and at the left we have the height of soil, and at the right we have volume of soil. If you apply a pressure on the soil, you can easily see there is a delta V, delta in volume of soil. If we just assume that change is just happen in the void ratio, so we can call V volume of void at the initial stage when there is no push, and as soon as you have a push, we have this much of settlement, and this is our new ratio from here to here. So we missing this part, and just assume V of S remains the same in all the process. So can define void ratio like volume of void over volume of solids, and if you add a 1 to both sides, it just goes to be like Vs at denominator, V plus volume void plus volume void plus volume S. It just in volume column is volume total, so we can call that volume T. So E plus 1 is equal to VT total volume of soil. If you rearrange this equation based off Vs is VT total over 1 plus initial ratio. So just remember this equation, we'll use it later on. So, and at the same time, delta in volume. So if this is our area and we want to calculate this much volume, that's definitely area times thickness. So that's consolidation settlement is height times the area. And delta V definitely is delta in volume of void. We already talked about that. We assume that delta V is just applies the void ratio of the soil, which is correct over the volume of solids. So, and from previous slide, if you remember, S is equal to V naught or initial V over 1 plus E naught, just derivative S is equal to over 1 plus E, and V, it just means initial volume, initial void ratio, and that's equal to A times H. V total is area times the height, which includes the entire volume of soil layer. So that's area times height over 1 plus E naught. And at the same time, with SC, consolidation settlement area is equal to delta V. If just replace delta V by this part, and then delta V, we just agreed upon delta V is the delta V void ratio, and that's equal to delta E times Vs. That's delta E times Vs, and Vs is equal to AH over 1 plus E naught. So that's delta E times Vs, delta E times AH, A times H over 1 plus E naught, which is a volume of solids. If you cancel out A from both sides, it just gives you SC, consolidation settlement, is equal to change in void ratio over 1 plus initial void ratio times the total height of all soil. This is the main equation for soil consolidation. Let's expand it a bit and more detail and specification of this equation. So if you get to a chart which in vertical axis we have the change in void ratio, so this is change in void ratio, and in x direction we have effective stress or pressure, that's sigma prime, we show it by P in a logarithmic scale. So if we look at the slope of this line, if we call that 1, P1 and E1 example, and this point is 2, 1, 2. So the slope of this line, which is C, is rise over run. So change in A, that's E2 minus E1, E1, call it delta E, and then a logarithmic scale normal log of P2 is log of P1. And if you expand that, so we can call that P2 is like initial P plus extra stress which apply to the soil. This one is just initial stress. So we just assume P2 is initial P plus extra stress, extra pressure, and this one is just P0. P1 is just the initial one. So these are just the different way you call it. And then our slope is rise over run. We can rearrange it minus slope like log of P naught plus delta P over P naught. And then as soon as we have this part, can replace it like delta E is C times delta E is C times the coefficient times a log of P naught plus delta P over P naught. So then we know this one and can replace all, let's say, delta E in the equation of settlement. So if you place this part over here, if you replace it in the main equation, it just gives you the comprehensive equation of consolidation. So if you replace delta E to the second equation and just rearrange it, it just says consolidation settlement is a coefficient times height of the soil layer 1 plus initial void ratio times a normal log of P naught plus delta P over P naught. So let's see how we can interpret this equation. So let's see the variation of delta E and logarithmic scale of effective stress. So in a soil, we can have two parts. PC, we'll talk about it, and just assume this line as a separation line. If you are before this line, you are in over consolidation soil, and you need to use this coefficient by C. If you're passing your limit line, we call that normal consolidation soil, and you need to use this equation. So again, if you are in the first part of our chart, use CS for your coefficient over here, CS, and if you are in the second part, you definitely will CC chart. At the same time, CC is a compression index, and that's equal to 0.009 times liquid limit minus 10, and we call that compression index. And CS is smaller, far smaller than, and then it's 1/5 or to 1/10 of CC, and we call that swell index. So based off the region you're working at, you just replace that coefficient to consolidation settlement equation. Let's talk a bit further about a consolidation. So what PC is, this limit line, we call that PC is the maximum pressure, maximum effective stress. That's effective stress. All of the pressure in terms of consolidation or in terms of sigma prime. Sigma prime C is equal to PC. Just show it like this, which a soil layer has experienced during its geological time life from the past to the present. So that's the maximum pressure which a soil handles or experiences during its lifetime. So based off our limit line, which is PC, we have three different scenarios. Case one, which is the soil is over consolidated. Consolidated means are first part. It means your initial pressure and your pressure plus extra pressure is not exceeding the pre-consolidation. It doesn't, all of your forces together, it's not exceeding the amount which soil has experienced before so far during its lifetime. So in that case, when P not plus delta P initial effective stress plus extra effective stress is less than pre-consolidation pressure, so then you are in case one, and definitely as we talked, you use CS, which is soil index for your equation, and that's our case one, and it's an easy one. And the second case is when your initial stress, initial effective stress is definitely higher than the maximum stress which soil has experienced so far, let alone P naught plus delta P. Initial P is higher than the pressure which soil has experienced so far. Definitely you are in zone 2, then you need to replace the coefficient compression index in your C for, so it's consolidation settlement equation. And the case 3, which is a combination of both of them, it just says 1 foot is in over consolidation ratio, so you need this coefficient to use, and the other one is just P naught plus delta P is just passing. So once you start your problem, you are in the over consolidation domain, which is 1 CS, and the second part you are in normal consolidation scenario, you need to use CC in region 2. So let's see how that goes. So we call this like a CS for the first time, which is we are in the first part, and our limit for normal log is PC, which is here, PC over P naught, the normal log, CS H times H naught over 1 plus E naught, and H naught is just the height of the layer. And then plus CC, we are in the second part, CC, and then we are log of P naught plus delta V over P naught over PC. So that's P naught plus delta V over PC and CC. So that's a part coming from normal consolidation soil, with the limiting part of P naught plus delta V PC, and other part is, let's say, over consolidation part, which start with CS over consolidation with the limiting of PC over P naught, normal log of PC over P naught. And if you add them together, it just gives you consolidation settlement. And this is a kind of combination of case 1 and case 2. And these equations cover all the consolidation equation, and that's a good interpretation of consolidation settlement equation. Let's say what is over, let's define over consolidation ratio, which we see that with OCR. Again, PC is the maximum pressure which a soil layer has experienced its geological timeline, and OCR over consolidation ratio is PC over maximum pressure which a soil experience over initial effective stress. We call that OCR. The higher the pre-consolidation effective pressure, the better the soil is. So if OCR is going to higher number, that's a good indication. And how that, let's interpret it in the other words, we can say the higher the gap between P naught and PC, initial effective stress and pre-consolidation, the higher this distance is, the soil has a more capacity for more consolidation or compaction. Thank you. Solve a numeric problem consolidation. So thank you.